So the protons are here because this is an excess of negative charge, and so you have this positive. But these protons are, in a way, connected with the SO3 groups. So to move these protons, we need some water. Why? Because water comes here and remove the protons as this H3O+. Okay? So this HO+ now can move through, and this may happen to the various groups. Sorry, I have something with my throat. So in a way, this is an assisted transport, because it's assisted by water. So you understand from this mechanism that water is necessary for the transportation. In fact, if you have one of these membranes dry, there's no transportation. Only when you add some water, it becomes to have some conduction. Okay? But you also understand that if you have 4 groups like this and 4 molecules of water, it's already a little bit too much because you are involved in all the groups, but it's still okay. But if the number of water molecules is 6, 7, 8, then the excess is not useful for the conductivity. And you have the membrane which is full of water. And it's not a good for the operation. So the water content is very important here. So for all these membranes, the proton conductivity relies on the presence of water. Okay, here you have a little bit more detailed model, better than what I made on the board. You see that these one are the main chain, and these are the groups, sulfonic groups, and you see that there are some protons here that can move by this water. And you see the water here are these gray molecules. So you need some water, but still you must have some, well, let's put it this way. We need some water, but not more than the conduction size. And you see that usually, forget DMC, we'll talk about that later, but usually for polymer membrane fuel cell, and here you see the acronym is PEMFC. You can use both acronyms. The one that we use is polymer membrane fuel cell, and PEMFC stands for polymer electrolyte membrane fuel cell, but it's just the same. And you see, as I say, we need a sulfonic acid for proton transport. And I don't really know what these are, but we have this very important thing. We have to use water for, is written here, induced phase separation. That means that we have to remove protons. And you see that, as I told you before, this main thing here, so this, as you see, these backbones are the fluoride base and are hydrophobic, while the pendant group, that are these ones, have this SO3H, which is the conducting group. So with water, this becomes H3O+, and this moves. Of course, we have some important features here, but also some big problems. The important feature are that the chemical stability, which is given by these backbones here, and the reasonably good proton conductivity, but we will see that this depends on water. In fact, the issues are the high cost, because these membranes are not really too easy to prepare, but still the cost is much higher than it should be, because all those companies want to make some profit. Now you understand that the proton transport depends on the hydration state, but we can have always some problem with fuel crossover. So the hydrogen, instead of reacting at the anode, can go all through the way to the cathode. And then at the cathode, instead of having reduction of oxygen, as we like, we are going to have a reduction of hydrogen, and this kills the cell. Also, the situation is a little bit complicated because because this is maybe one of the pendant group. You see with the SO3 groups, and they are when you have to pass from one group to the other to allow maybe the jump of a proton, you must go through some very narrow channels. Okay. So you see the distance between the two sides may be of 5 nanometers, but the width of these channels is only 1 nanometer. So these membranes are very complicated, because suppose that the channels are in some way obstructed, then you don't have conductivity anymore. Here in this graph, the conductivity in terms of Siemens over centimeters are reported in terms of water content. As I told you, when the water content is 0, a dry membrane, the conductivity is not existing. So the conductivity increases when you have about 20. This lambda means the number of water that you have for number of available sites. So let me see, 20% is the best. All the other waters may also go here and close these channels. So this lambda is very important, because it's giving you the right amount of water. But you have to remember the water is the product of the reaction. So you have a lot of water forming during cell operation. Okay? And so you have somehow get rid of this water. Now let's see the other point here, and it's the catalyst. You remember that we need a catalyst to have operation, both hydrogen oxidation and oxygen reduction. And we know by now that this catalyst is based on platinum. And these, of course, are platinum is a rare metal, and it is very expensive. So another issue is the cost. Okay, how can we reduce the cost? Well, we can reduce the amount of platinum. One thing that you have to remember is that the catalyst is not taking part of the reaction. The catalyst is there only to favor the reaction. Remember, the platinum is absorbing some hydrogen or oxygen and then release the hydrogen and oxygen. So the platinum is not consumed during the reaction. So we can have a good catalyst also by using just the platinum which is sufficient for the reaction. And how can we do that? We can have a very large surface substrate, for instance carbon, here. You see? This one. This is a high resolution transmission electron microscope. and disperse on this very high surface area some particle of platinum. You see the particles here. This being a very high resolution transition electron microscope, you can even see the atoms of the platinum. So you have very small particles here. And these are the particles which are doing the work, the catalyst work. And at the beginning of some years ago, but not very many years ago, the amount of platinum was 0.5 milligram per square centimeters, a lot of platinum. And if you have 0.5 milligram per square centimeters, and you want to use fuel cell for driving a car, as we will see later on, there is not enough platinum in the world to do that. So this amount has to be reduced, and by this nanostructure assembly, the platinum load can be reduced. And you see here, oh sorry, I made a mistake. It was not 0.5, was 5 milligrams per square centimeter. So in 1997, which is not far ago, long ago, but the platinum content was 4 milligrams per square centimeter. Very much not acceptable, too expensive and not useful. And then in 2002, it went down to 0.1. And today, still at the laboratory result, this is even lower. Why we have this big change between 1997 and 2000 and today? Because at the beginning of the year 2000, fuel cells were very popular, and the various governments devote a lot of money for fuel cell research. And this was the results. Oops. At that time, all the money for research went to fuel cell and no money for lithium batteries. It was a big mistake. Now it's the opposite. A lot of money is going to lithium